Welcome to the screencast on determining whether a function has an inverse function. To begin, let's review the definition of a function and what it means for a function to have an inverse function. So we know a function is a repeatable process that takes a collection of input values and generates a corresponding collection of output values with the property, and this is key, that if we use a particular single input, the process always produces exactly the same single output. And we can determine whether or not a given function f has a corresponding inverse function by determining if the process that defines f can be reversed, so that we can also think of the outputs as a function of the inputs. So in other words, f is a function if every input is paired with exactly one output, and the function f has an inverse if every output is paired with exactly one input. It's important to notice that f has an inverse if, right? So that means there's not a guarantee that an inverse function exists for a given function. So let's practice determining if some different functions defined by tables and graphs have inverse functions. So the directions say determine with justification whether functions p and q have corresponding inverse functions, and if so, give an example of values of the inverse function. So first, we know p of t is a function because for any particular input, there's exactly one corresponding output, but in order for p to have an inverse function, we have to reverse the process. So we're going to consider as inputs 3, 5, -2, 6, and -1. And we're going to consider as corresponding outputs -2, -1, 0, 1, and 2. And we see that from this new perspective, this reversed perspective, each input corresponds to one and only one output. So p has an inverse function. And from our previous knowledge, we know that if p of 1 equals 6, then we can also say that p inverse of 6 equals 1. So that's our example of a value on the inverse function. Now let's look at q of t. So q of t is a function because, again, for any particular input, there's exactly one corresponding output. In order to determine if q has an inverse function, we'll reverse the process. So we're going to consider as inputs now 3, 5, -2, 5, and -1, and the corresponding outputs will be -2, -1, 0, 1, and 2. And from this reversed perspective, we see that 5 corresponds to two different values, -1 and 1. So while q is a function, q cannot be reliably reversed, and so q does not have an inverse function. So it won't even make sense to give an example of a value on the inverse function because q does not have an inverse function. All right, now let's look at two examples where the functions are represented graphically. On the left, we see the function h. We know h is a function because its graph passes the vertical line test. That is, any input value used to sketch a vertical line intersects the graph of h exactly once. So any input is paired with one and only one output. And if h has an inverse function, then by reversing the process, every output must correspond to one and only one input. So let's look at the output of, let's say, y equals 0.5. We see that 0.5 corresponds with more than one input. In other words, because the horizontal line y equals 0.5 intersects the graph of h more than once, h does not have an inverse function. All right, and on the right we see the graph of w. Function w passes the vertical line test. Even at t equals -2 and t equals 3, the only corresponding outputs are 2 and 1 respectively. Function w does have an inverse function because for any choice of output, y, there's one and only one corresponding input, t. Even at y equals 1, the only corresponding t value is 3. And at y equals 2, the only corresponding t value is -2. So another way to look at this is to notice that any horizontal line representing any output of w will always correspond to one and only one input of w. Thus, w has an inverse function. So in this case, it would make sense for us to say something like, since w of 3 equals 1, from another perspective, w inverse of 1 equals 3. The graphical observations we made from these functions provide a general test that we call the horizontal line test for whether or not a function given by a graph has an inverse function. The horizontal line test states that a function whose graph lies in the xy plane has a corresponding inverse function if and only if, that means this must happen, every horizontal line intersects the graph at most once. When the graph passes this test, the horizontal coordinate of each point on the graph can be viewed as a function of the vertical coordinate of the point. In the next video, we'll look at how to determine if a function determined by a formula has an inverse function.